Welcome to MRS Bulletin. My name is Priscila Cavassin, and we're meeting today with Ottman Tertuliano, AMA Family Assistant Professor of Mechanical Engineering and Applied Mechanics at the University of Pennsylvania. Ottman received the MRS Graduate Student Award and Arthur Nowick Graduate Student Award in 2018. Ottman, thank you for meeting with us today. So first, could you share with us what is your research area?
Yeah, absolutely. So we're really excited about how mechanics drives structural biological systems, right? What's really exciting about structural biological systems, unlike a lot of engineering systems that we have, is that they're living, so they adapt over time. They are really lightweight, they're strong, they're robust, and they're really resistant to fracture, right? So they're resistant to cracking. And one of these systems that I personally really care about is bone, right? So it is the fundamental sort of scaffold that enables us to run around, play with our kids, maybe me waving my hands like this, right? Without anything cracking. And how that happens is through sort of a separation of time scales, right? So there's the tissue component, which is like a nice material composed of like collagen and calcium phosphate. And then there's a sort of the cellular component, which is the living aspect that comes in and is continuously fixing the material aspect, right, over long time scales. And how exactly this works in order to create a system that is going to hold us up for 70, 80, 90 years is not really well understood. And it's all really starting at the fundamental nanomechanical length scales, right? So the constituents are nanoscale. They resist fracture at the nanoscale, and they are remodeled at the nanoscale. So we're really taking this interesting approach of like all of the fundamental nanoscale mechanics that we've learned from like inorganic materials and semiconductor materials and the tools and the characterization methods, and we're applying them to tissues to learn something that biologists right now simply can't do. So a lot of borrowing from material science, mechanics, and characterization, and then applying it to mechanics of tissues at small length scales.
Thank you so much. Okay, I'll go in. Thank you. And I would also like to ask you, what motivated you to pursue a career in this direction that is very much involved with materials research, right?
Yeah, so it's actually interesting. When I first started off, I started working with graphene as an undergrad at Columbia. And I was working with a tribologist, so this is a study of friction, wear, and lubrication. And we were working on graphene alongside another faculty there, James Hone. And it was around the time that James Hone and his group had measured basically the intrinsic strength of graphene. And he had this really beautiful quote about an elephant on top of a pencil, sort of being needed to puncture graphene. And I got really pulled into this idea of materials having fundamentally different properties at nanolength scales and how we can really start to use that and scale that up in beneficial ways. Now, that sounds really different from what I described earlier about understanding fracture and bone, but I got pulled into moving from purely a mechanical engineering undergraduate degree to sort of a more fundamental material science degree. And that's sort of actually how I got into doing a PhD with my advisor, Julia Greer at Caltech. So we started thinking about really interesting problems in nature. Those that had really complicated architectures, so bone being one of them. And it turns out there was this really, really big hole in our understanding of how systems that have complicated architecture across length scales, really spanning from like the molecular level to the nanoscale, to the microscale, and even like to what you would consider like a whole organ, right? Like your femur. Things that have really different architectures at each of those length scales. How do they mitigate sort of mechanical stresses? That's how we got pulled into this problem, really.
Thank you. And what would you say were the main challenges that you faced getting up to this point where you're now?
Ooh. I mean, I would say we have a variety of problems. So there are the more technical challenges. So when I started working on mechanics of biological tissue is really sort of asking the question, right? So how does mechanics drive biology? I started in the group that had zero biological experience. So we were really thinking about fracture from a purely material science point of view. So the analogy that I made earlier to a bridge, right? That's really how we were thinking about it. And we had not brought in this idea that these systems were living and engineered over long time scales. And, that I think to some degree limited how I think about like developing nice sort of mechanically robust systems that are meant to interface with the body. So that's taken time to sort of relearn, and I would say actually learn biology that's informing my material science and mechanical engineering research. That's on a technical aspect. On a non-technical aspect, I mean, I was doing a lot of this, I would say through COVID. Right, most of my postdoc was through COVID, and I think I faced a lot of the same challenges as everyone else.
How would you say to someone how to find someone to really change your work and your advancement in the field?
Yeah, so I got really good advice when I was an undergrad, and I was deciding where to go to grad school. So I was working for the entire time as an undergrad with this PhD student, Emil Santos Rosado. He's now a senior scientist at ARL, Army Research Labs. And he gave me advice that, one of the things you can do is try to find someone who's really, really excited about a problem. So at that stage, I knew I was excited about doing something fundamental, right? Having come from like a very sort of hands-on mechanical engineering background. But I wasn't exactly sure what fundamental problem I wanted to tackle. So in interviewing, I was really looking for someone who was like super high energy and super excited about the types of problems that they were working on. And I knew that if I could come in, feed off of that energy, and also like show that I could carry that somewhere, this would be a good mentor. That's actually how I found my advisor, Julia. And we just resonated really well. I think there's a lot of like trusting your gut when having a meeting and interviewing with someone. And then it helped that I think I was at the time and still am just very motivated, right? Like there was a lot of running into obstacles. Maybe this is fitting into your previous question, right? The challenges. There are a lot of running into technical obstacles, but showing that, I was not willing to stop, and like getting continuous support from a person like that was really useful. And it turned into great results. It turned into them. I think there's a feedback loop between like someone championing your work and you sort of being someone that people want to champion, right? Like you really have to show that you want it. And I think at the time I was showing that I really wanted it. Yeah. I want to add actually one more thing. So that was at the grad level stage. Of course, I had really wonderful advisors during my postdoc as well, right? It's going to feed into your maybe potentially next question, but I remember talking to someone when I was interviewing for faculty jobs, and they made the distinction between sort of mentorship and sponsorship, where mentorship is often what we really think about, right? You can talk to someone more senior and they give you advice, but also sponsorship, which comes from someone who's willing to put their money where their mouth is when it comes to sort of endorsing you. So putting you on grants, right, funding you. So those have been, I think, really beneficial relationships that I've developed, right? So I've had, particularly during my postdoc, right, I had some rough points, but I had people who stuck with me in terms of like continuing to fund me for those 3 years. So.
Thank you. Yeah, I think that's great advice for younger researchers. Also, you received the award for the MRS graduate student and the Arthur Nowick Award. How would you say that, how did they impact your career so far up to this point?
Yeah. Oof. Okay. There are a couple of ways. One is the preparation that it took to be competitive for those. So I recall actually practicing my talk before, maybe like a week or two before going up to MRS and Phoenix and presenting. And I remember getting a lot of feedback. And I had to completely change how I was telling my story. And I spent basically, the next 2 weeks not sleeping and like really homing in on how to give that 10, 15-minute talk. And that was a really formative experience, right? Because it really changes how I communicate about science. Maybe this interview isn't the best example, but it really changed how I sort of told my story in terms of understanding fracture and tissues. But um, beyond that, like once actually getting there, meeting people like Zach has been really nice. So I met Zach, wow, 6 years ago, right? So now we're closing in the loop on this idea. So making colleagues and friends who are going through that training behavior or that training process with you and are staying in material science like for decades to come, right? Helps build community. So that's been nice. And then maybe lastly, on a more tangible note, the timing for those awards was great because I was applying for a postdoctoral fellowship at Stanford at the time. I had already submitted my application, and I think it was under review, but I won these awards like before I'd heard back. And I remember my advisor at the time, so maybe it goes back to how do you find someone to champion you? Yeah, I remember getting back to Caltech, telling my advisor, she was happy, and she said, "Oh, you can actually just contact Stanford and update your CV. Tell them that you've won these awards. That'll make you more competitive." And I don't know to what degree it helped me get the job, but I can't imagine that it hurt. So the timing was great, right? So the preparation to win it, I think, was useful. The community that it helped me build, and then the direct opportunities that it opened for me immediately after. So I think MRS was in March or April, and then I started the job in September. So that's great.
Thank you. No, it's really great to have this insight that it's not only the award itself, but the preparation for the award and the people you meet in the way, and how all of these things matter.
Yeah, and interestingly, there are a number of other obviously there's some people who won, some who didn't, but everybody there was an incredibly talented scientist, and you could see sort of like the amount of effort and amount of work that other students were putting into their work, and it was extremely motivational. Yeah, so just participating honestly is incredibly beneficial.
Thank you so much. My name is Priscila Cavassin. For more news, go to mrsbulletin.org and find us on X, MRS Bulletin. Thank you for watching.